Why does a rolling ball always slow and stop? Why do you lurch forward when a car suddenly brakes? Why can a rocket push itself through empty space, with nothing to push against? The answers to all of these come down to three simple rules, written over 300 years ago by Isaac Newton. They're called Newton's laws of motion. And once they click, you'll see them everywhere. First, a quick foundation. In physics, a force is simply a push or a pull. Forces can speed things up, slow them down, or change their direction. Nothing changes its motion on its own without a force. You meet forces all the time. Gravity pulls everything toward the earth, it's what makes a dropped ball fall. Friction is a force that resists motion when surfaces rub together, it's why things slow down and stop. Scientists even measure forces in units called newtons, named, of course, after Isaac Newton himself. Newton's genius was to figure out the exact rules that forces follow. Let's take them one at a time. The first law is all about a property called inertia. It states, an object at rest stays at rest, and an object in motion stays in motion, unless a force acts on it. In other words, things keep doing what they're already doing. They resist any change in their motion. So why does a rolling ball stop? Because a force is acting on it, friction, rubbing against the ground. Out in space, with almost no friction, a tossed object would just keep going, in a straight line, forever. You feel inertia in a car. When it brakes suddenly, your body keeps moving forward, which is exactly why we wear seatbelts. And the classic trick, yanking a tablecloth out from under the dishes, works because the dish's inertia keeps them in place. Here's a key idea. The more mass an object has, the more inertia it has, the harder it is to start or stop. That's why it's easy to stop a rolling tennis ball, but nearly impossible to quickly stop a rolling truck. The second law connects force, mass, and acceleration. It can be written as a simple equation. Force equals mass times acceleration. Force equals ma. In plain words, the harder you push something, the faster it speeds up. And the heavier an object is, the more force you need to get it moving. Picture a shopping cart. An empty one is easy to push and speeds up quickly. But load it up with heavy bags, and the same push barely gets it going. More mass means less acceleration. This is why a light soccer ball flies when you kick it, but a heavy bowling ball barely budges from the same kick. The second law also clears up a common mix-up, mass versus weight. Mass is how much matter is in an object, it never changes. Weight is the pull of gravity on that mass, so on the moon, you'd weigh less, but your mass stays the same. Force, mass, acceleration, change one, and the others respond. That's the second law. The third law is the most surprising, and the most fun. It states, for every action, there is an equal and opposite reaction. Whenever one object pushes on another, that object pushes back just as hard, in the opposite direction. When you walk, you push backward on the ground, and the ground pushes you forward. When you swim, you push water backward, and the water pushes you forward. Let go of a blown-up balloon, and it zips away. The air rushes out one way, pushing the balloon the other. One important note: the two forces in a pair always act on different objects, which is why they don't simply cancel out. And a rocket? It pushes hot gas downward with tremendous force, and that gas pushes the rocket up into the sky. That's how rockets work in empty space. They don't push against the air, they push against their own exhaust. Action and reaction, always equal, always opposite, always in pairs. Now let's see all three laws working together. Imagine kicking a soccer ball. At rest, it stays put. That's the first law, inertia. Your kick applies a force, and the ball accelerates away. The second law, force and mass. And your foot feels the ball push back against it. The third law, action and reaction. Three simple laws, hiding inside a single, ordinary kick. So why do these laws matter? Newton's laws explain almost all the everyday motion around you, from walking to driving to playing sports. Engineers use them to design cars, bridges, airplanes, and safety features like seatbelts and airbags. And they took us to the moon. Every rocket launch is Newton's third law in spectacular action. These three rules, written centuries ago, still guide our entire modern world. Once you know the three laws, you start to see them everywhere you look. In a car, all three appear at once. Press the gas, and a force accelerates you. That's the second law. Turn a corner, and your body leans outward, wanting to keep going straight. That's inertia, the first law. Brake hard, and your seatbelt and airbag apply the force that slows you safely. In sports, a harder swing or a heavier bat sends the ball farther. Force, mass, and acceleration in play. A swimmer, a rower, and a jumping athlete all push against something to move. The third law at work. Long before Newton, Galileo had shown that objects keep moving unless something stops them, laying the groundwork. Newton pulled these ideas together into three clear laws that still describe almost all everyday motion. There's even a related idea called momentum, how hard a moving object is to stop, which grows with mass and speed. Let's recap. First law, objects keep doing what they're doing unless a force acts. That's inertia. Second law, force equals mass times acceleration. More force, more acceleration, more mass, less. Third law, every action has an equal and opposite reaction. Master those three, and you understand the basic rules of how everything moves. From a rolling ball to a rocket to the moon, the same three rules are always at work. And now you can see them. Thanks for studying with us. If Newton's laws finally make sense, stay with us. There are many more science topics made clear and simple. Until next time, keep asking questions, keep learning, and you'll be amazed how much you can understand.